All right. Thank you for showing up. Hello. Clearly you see some value in the lecture, so thank you for that. Why not go on Quarkus and fill out the course evaluation? So while you're there, there's a quiz. It's not one of the harder ones. I did not come up with a good question. So, okay. All right. So, like, whatever like Mr. Weisstein thinks, we also have programming content to do. So I am gonna just go ahead with a not super easy lecture today. Hopefully you're watching on YouTube. I don't know. So the plan is basically like this. So we'll do one or two more recursion examples with complexity analysis. And for now, we're honestly doing stuff that you could probably do with a for loop and would be easier to do with a for loop. But at least we'll start. I don't know if we'll be able to finish today, but we'll start doing merge sort, which actually is much harder to do without recursion. So for now, we're doing stuff that honestly you could do without recursion as well. So I'll do log 10. And this is, so return log 10n. Assume that n is a power of 10. So the way we had done it before with a for loop was we repeatedly divided n by 10 and counted how many times we had done that, right? What I want to do now is do it the other way. So it's actually kind of similar to the repeated squaring anyways. So what's the math here? Well, the math is 10 to the power of n plus 1 is equal to 10 times 10 to the power of k, right? So 10 to the power of k plus 1 is 10 times 10 to the power of k. And what that means is log 10 of 10 to the power of k plus 1 is equal to log 10 times 10 to the power of k, so just logs of both sides. And then what's log 10 of 10 to the power of k plus 1? That's like asking, I have the number 10 to the power of k plus 1. What power do I need to raise 10 to in order to get that number, 10 to the k plus 1? The answer is k plus 1, right? So this is just k plus 1. Does that make sense? Just because one way to think about it is power is just the inverse operation for log. The other way of thinking about it is just like in English, what power do I need to raise 10 to in order to get this number? Well, k plus 1 is the answer, right? And then this, I did not say log 10 here. This is log 10, 10 plus log 10, 10 to the k. And that is also 1, right? So log 10, 10 is 1. And that is k. So that works out. So from that, what can we say? Well, we can say that log 10n would be 1 plus log 10 and divided by 10. Does that make sense? So it's basically this. So that gives us the recursive step. I can just say I want to return 1 plus log 10 and divided by 10. To be clear, so this might not be super clear. So that's just how logarithms work. Okay, is this good with everyone? Okay, so we need a base case. So the base case would be what's log 10 of 1? That's 0. So 10 to the power of 0 is 1. This returns 0, and that is that. Make sense? So again, like we just have this mathematical property where log 10 of n is just equal to this. And then we have the base case, which is n to the power of 0 is equal to 1. So log 10 of 1 is 0. So we know the answer right away. Make sense? So let's say that we want to analyze the complexity of this. So the call would be like this. So you call it with log 10n, and then you call it with n over 10. And then you call it with n over 100. And then you call it with n over 1,000. And so on. And when do you stop? Well, you stop when you call it with 1. Right? So now we want to know essentially how many calls. So we kind of did that when we analyzed the iterative version of the log function. It's the same idea because basically the number of calls is just your answer. The way to see it is you're counting how many calls there are because you're returning 1 plus every time. So how many calls? Well, you go from n to n over 10 to n over 100 to n over 1,000 and so on down to 1. We invert it. So we say we start with 1, which is 10 to the 0. And then we go to 10 to the 1. And then we go to 10 to the 2. And so on up until the point where we get to n. So the answer is like how many numbers in the sequence. And the answer is, well, if n is equal to 2 to the m for some m, then there are, sorry, 10. Then there are m plus 1 calls in total. Right? And the reason is you start with 0, then you go to 1, then you go to 2, and so on. And then you go to 10 to the m. In total, there is m plus 1 calls because there is also the call to 10 to the 0. So the only question is, what is m? Take the log of both sides. M is log 10m. Right? So that means there are log 10 of n plus 1 calls in total. So the complexity is O of log 10 of n, which is actually the same as just O of log of n. And that's just because it doesn't matter what the base of the logarithm is, right? The reason it doesn't matter what the base of the logarithm is log 10 of x, so this is just an aside, is equal to log of x divided by log of 10. Log of 10 is a constant. The log, you don't even care, is it like log base e or log base 10 or whatever? It's going to work for whatever log there is. So ordinarily, we just write O of log n, and we don't even care, like, is it log base e, is it log base 10, whatever. They're all proportional, with the constant proportionality, in this case being 1 over log 10. Make sense? And kind of, this was just for the sake of the example. The other way of saying it is, how many calls are there? Well, what we're doing is we're adding 1 plus every time that we do a call. What we want to know is what's log 10n. So basically, there is approximately log 10n calls. There's nothing more there. All right. So, okay. So I want to review this as well as 2 more mathematical facts that are like the 3 mathematical facts that we are going to need to use in order to analyze at least the examples in this class, except for one. So the facts are, and those are the facts that you need to know, what we had just said. So 1 and then a to the 1 and then a to the 2 and so on up to n. This is approximately log a n steps, right? This is just what we had done just now. The other fact is the arithmetic series. So this would be 1 plus 2 plus 3 and so on plus k is equal to k times k plus 1 over 2. And the other one is the geometric series. And that is 1 plus r squared and so on plus r to the k is 1 minus r to the k plus 1 divided by 1 minus r. Those are things that you do need to know for the exam. I'm not giving those out during the exam. When I was an undergrad, would occasionally just like take the subway to the exam center and like on the subway, like repeatedly write down the things that they couldn't remember before, and then just like come into the exam, and like first thing that I do when I open the exam is I just like write the formulas that they didn't want to remember. That is allowed if you want to do it. However, knowing those formulas is useful in life, so might as well know them now. Okay. So, all right, let's do a warm-up example now. That is going to be the sum list example from the other day. So the idea here was So the idea here is sorry, I meant to actually repeat it squared. So this is power xn. Sorry about that. So the idea here, this is kind of analogous to sum list 2. So the idea here is we compute the half power. And the half power is x divided by n over 2. X to the power of n over 2, sorry. And then if it's even, we return half power times half power. This is something we already did. You did not need to copy it. And else we return that times x. And then we have okay. So that is what we wrote. And if you remember, that was also logarithmic. So what they mentioned is that if you don't do this trick where you just compute the half power the once, it would be different. So let's do that. So I'm just copying this. Okay, I take back that you didn't need to copy it because I'm now going to modify it. Okay. So instead of saying half power, I'm just going to plug in power x times n over 2 like so. So intuitively, that takes more steps because you're just calling power x to the power of n over 2 several times when you could do it the once. So what I want to know is exactly how much slower is it, right? So let me do the call tree. I will omit power x n over 2. I will just plug in like the n. So we start with n. And then we do 2 calls, right? So we do 1 call with n over 2. And then we do another call again with n over 2. And then we do 2 calls here. So this would be n over 4. And this would also be n over 4. And similarly here, you'll have this. And so on. Eventually, you stop when you get to zeros. So again, we want to ask how many calls is that, right? So the question that we're trying to solve is, every n over 2, n over 4 there, that represents a call. The number of calls is proportional to the runtime. We want to know how many calls there are in total over there, right? All right. So let's see how many. So here's a trick. What I'm going to do is I'm going to count the calls level by level. So what I mean by that is I'll say on this level, there is 1 call in total. And then on this level, there's 2 calls. So level is not like a programming concept. Level is just like in this picture, there's levels. And then on the next one, there's 4. And then how many are there here? Well, this is 2 to the 0, and this is 2 to the 1, and this is 2 to the 2, and so on. So this one is 2 to the k for some k. Right? And then k would be the total number of levels. How many levels do I have? Well, as many as it takes to get from n to n over 2 to n over 4 to n over 8 and so on down to 0. Which is? Anyone? So how many steps if I go? Yeah, log to n. Yeah, log to n plus 1. Yeah. Why? Well, because it's again the same pattern, right? So I go 0 and then I go, so this is like So this is like all zeros, and then this is like all ones, and then this is like all twos, and then all fours, and then all eights, and so on up until the point where I get to n. So it's the same pattern. It is +1. I'm not going to worry about the +1s, -1s because they don't matter. But that's, again, it's log to n levels. So, okay. So k is equal to this. But that doesn't answer how many calls. That answers how many levels. So how many calls? Well, it's 1 + 2 + 4 + 8 and so on, plus 2 to the power of log 2n plus 1. That is a geometric series, right? So that is equal to just plugging in the formula. I'll copy this. So this is this. So this is 1 minus this whole thing plus another 1 divided by 1 minus 2. So divided by 1 minus 2 just means flip this. So this is this thing minus 1. And 2 to the power, and then 2 to the power of log 2n is just n, plus 2 is just times 4. Make sense? Questions? Was that too fast or is that okay? Seeing no objections. So that works out to 4n. So that means that the number of poles is proportional to n. So the slow power function runs in O of n time. All right. So basically, if you remember, it was O of log n if you did the efficient thing and computed half power the ones. But because this tree kind of starts branching out, it turns out that there is a number of calls that's proportional to n at the end. Cool. And it's kind of a nice pattern. So this is like one of the patterns you see. Like it kind of looks like it shouldn't be n because it's like branching out. So you would think it's more. But the thing of it is that there is like not very many levels there. There's just log to n levels. So even though it looks like it's branching out, most of the calls are just over here. So for that reason, it's actually proportional to n because there's not very many calls and it gets wider very fast. So that's just the intuition. The math just says it turns out to be O of n. Make sense? Let's do another one. Let's say that I want to compute 2 to the power of n. So multiple ways of doing it, but here is like a silly way of doing it. I can say that 2 to the power of n is equal to 2 to the power of n minus 1 plus 2 to the power of n minus 1. Like that's true, right? So that means that I can just write it. And now we need a base case. So that's a good base case. Well, if n is equal to 0, then it's 1. Make sense? So it doesn't look super efficient, but it's mathematically true. Right? All right. Let's see what the tree looks like. So we start with n, and then that branches out, and there is a call to n minus 1, and then there is another call to n minus 1. And then there is a call to n minus 2, and another call to n minus 2. And so on. And then there is a bunch more until you get to zeros. So again, we're going to ask how many calls in total, and we're going to use the same trick. We're going to count them level by level. So there is one call over here. And then there is 2 over here. And then there's 4 over here because each one spawns 2, right? So if there's 2 over here, then each of the 2 spawns 2, so that's 4. And then eventually you get to here, and again, we have 2 to the k calls over here, right? So, okay. What is k? So k is the number of steps to get to 0 from n by subtracting 1 every time. That's not a very difficult math problem, right? That number of steps is n. Make sense? So really, this is 2 to the n. So how many calls in total? So this is, again, the geometric series. So the runtime here is O of 2 to the power of n. All right, so not super fast. So note that superficially, this seems like the same kind of shape, but it's a lot more calls, right? The reason it's a lot more calls is there's a lot more levels. So here we go in steps of -1. Previously, we went in steps of divided by 2. So that makes a difference between O of n, which is, reasonable, and O of 2 to the n, which explodes very fast. Make sense? Okay, so that was the warm-up. I now want to actually do something substantive with all this machinery. And the something substantive is merge sort. So that's and that is what Python uses pretty much. So Python uses like a variation of merge sort, actually, not literally merge sort. So the idea of merge sort is like this. So to sort a list L, what I can do is I can sort the first half and then sort the second half of L. And then merge the lists to get the sorted version of Alice. That's the idea. Okay, so if I have a list that's not sorted initially, something like this, what I'm going to do is I'm going to say sort the first half. So the first half would be whatever, like 5, 1, 10. And then sort the second half. So that would be 20, 125, 7. And then once I have the sorted versions, so once I have 1, 5, 10 over here, and I have 7, 20, 125 over here, I'll merge them into one big sorted list. And you can kind of see that merging those can be pretty fast, right? So you can, of course, do the silly way of merging them by just like stick them together, sort the whole big thing. That might be slow. But what you can do instead is you can say, okay, so I'm just like building up the merged list. And the way I'll do it is I'll say, well, like, you know, like it's going to be like 1 and then 5 because 5 is still smaller than 7. And then I'll have 7 and then I have 10 because that's smaller than 20. And then I'll have 20 and then I'll have 125. So you can kind of see that I could type it out fast. The reason I could type it out fast is because I basically have this is sorted, this is sorted. I'll like interleave them correctly so that the whole thing is sorted. Make sense? So, okay. So let me first write the skeleton for merge sort, and then we'll write the merge function, and then we'll analyze the complexity. So I'll have my, whatever mid. So I'll call merge sort the thing that sorts L on the first hop. And I'll call it on the second hop. And then I'll have a helper function merge that's going to merge the two sorted parts. Is that so? Like just like mathematically, it should make sense. Like without thinking about the kind of the mechanics of what exactly is going on. Sort the first half, sort the second half, interleave them so that the whole thing is sorted. You're done. We need a base case. So if the length of L is more or equal than 1, then the list is already sorted. An empty list is always sorted. A list of length 1 is always sorted. So I'll just return a copy of L. The reason I'm returning a copy rather than L itself is just because I want to make sure that I always return a fresh list rather than sometimes returning the alias and sometimes not. So that's just like for symmetry. Right? So that's merge sort. That's all it is. The basic idea is merge the first half, merge the second half, interleave. So what's left to do is to write the merge. So you could, of course, do something like this. Like this is valid Python, it would work. So like stick them together and sort them with the built-in sorted. The problem with this is slow because this doesn't use the fact that L1 and L2 are actually sorted. Right? So how do we keep track of, how do we kind of sort them efficiently? Well, what I'll do is I'll say, okay, I'll keep track of where I am in the first half, and I'll keep track of where I am in the second half. And then I'll just keep building up the result by, I'll put in 1 and then I'm over here. And then I'll put in the 5 and then I'm over here. And then I'll put in the 7, so I'm over here. And then I'll put in the 10, so I'm done here. And then I just do, okay, so insert the 20, insert the 125, and then I'm done. So, okay, so that's what I'll do. So initially I wanted 0 and I2 is 0. So this is the location inside L1, and this is the location inside L2. Right? And I'll just keep going through the 2 halves that I broke off and merging them. So, okay. So I'll put in my condition later. So here, like I'm somewhere here, like maybe I'm here. I need to basically ask, should I include L1 at A1 or L2 at A2? Which one do I include? Well, the one that's smaller. So if L1 at A1 is smaller than L2 at I2, then I append L1 at A1 and I advance I1 by 1. Otherwise, I do the other thing. I append L2 at I2 and I advance I2. So when do I stop? I stop when either I cannot look up L1 at A1 because I1 has gone out of bounds, or I cannot look up L2 at A2 because I2 is out of bounds. So while I1 is smaller than length of L1, and also I2 is smaller than length at L2 of L2, I can keep going on. When one of those is done, I cannot do the loop anymore. So at this point, what happened is the loop is done. So that means either I exhausted L1 or I exhausted L2. Those are the 2 reasons that I would be done. So what I'll do is I'll just say, okay, I don't know which of L1 or L2 is done. Kind of doesn't matter because all I need to do is just exhaust the one that's not done until the end. So I'll just say, this, and I'll say this. So one of those is not going to happen because the reason I'm over here is I exhausted one of L1 or L2. But the other is going to happen, and what I want is to exhaust it, right? So I'm done. Just return result. Does that make sense? And this is merge sort. So that's it. So the beauty of it is that the recursive call itself is nothing. It's just like sort the first half, sort the second half, merge, done. And then the merge, like it's a little bit annoying to write, but it's not very much, right? It's like whatever. And then it turns out that it's really fast. So how do we analyze it? Let me first do the calls. So the notation here is like I'm going to try to make it as non-annoying as possible. So this means a list of length n. So it's kind of not standard, but that's like the best I can do. And then that produces 2 calls to 2 lists of length n over 2. And then each of those produces 2 calls to lists of length n over 4. And then eventually it's all lists of length 1. All right. So the first thing I'll do is I'll ask how many calls. That is not actually going to be what the complexity is. So how many calls? Surprise, surprise, I don't actually need to do the derivation. We already did this example 30 minutes ago, right? So this is exactly this, right? So how many calls, like proportional to n? So because we already did exactly this example. But that doesn't answer what the complexity is. The reason is that different calls take different amounts of time. Why is that? Well, because I'm calling the merge here, and the merge actually takes longer if the inputs are longer. What the merge does is it basically builds up a list of length n, where n is the length of the first half plus the length of the second half. So if the list is longer, that is going to take longer. Okay. So the trick here is going to be, okay, like we answered how many calls, but that doesn't answer actually how much time. So what does answer how much time is, okay, so how much time spent on each level? And the answer is merge takes time proportional to length L1 plus length L2, right? And that's just because all we are doing here is we are eventually appending length of L1 plus length of L2 elements, right? So on each level, what do we do? So here we call merge on n elements in total. And here we also call merge on n elements in total. And here we also call merge on n elements in total. It's just that we do it in smaller parts. So the answer is each level takes time proportional to n. I will do it in more detail next time, of course. So the spoiler here is there are log to n levels. So runtime is proportional to n times log n. So two things about it. One, that is remarkably fast compared to whatever, like selection sort, bubble sort, the kind of thing that you might come up with if you just think about it for a bit. Like n squared, again, kind of that might be belaboring the point, but 1,000 squared is a million. 1,000 times log 10, 1,000 is, you know, like log is like 3,000. So that's a huge difference. It is kind of weird that the log comes up. You can kind of see where it comes from, but yeah, like it's a sorting algorithm and somehow the log comes up. So a more detailed analysis is coming up on Tuesday when hopefully everyone will be, when's MATLAB? Is it Tuesday? Oh my God. Okay. Well, okay, got to learn sometime. Okay, all right. Good luck with everything. I will see you next week. Bye.